Welcome back. So we left off talking about the past evidence of movement and current proof of movement of plates. What's driving that? What's creating that movement? That's what we're going to talk about. So this is the Earth. All of these lines represent the plate boundaries. So there are a number of different fragments, some large, some small, but each of these are the plates. For instance, this is the Pacific plate, a very large plate. See, most of the United States and North America sits on the North American plate. Go figure. This is the Eurasian plate because Europe and Asia kind of sit on it. So in any case, not all of them are named kind of as intuitive of that. But in any case, what you see here, these are the boundaries between different plates. This little plate right here, the Juan de Fuca, is a small but mighty plate. More on that at a later time. But in any case, plate tectonics is the movement and an interaction of large fragments and a number of small pieces of Earth's lithosphere. Just a fancy word for the crust. So, there's evidence that plates move, but how and why do they move? That's what we're going to talk about. How and why do they move? Just remembering back, we have the solid inner core, we have the liquid outer core, we have the mantle. The mantle is broken up into a few different pieces, but for the context of this class, we can just consider the mantle just kind of one large big area. It's actually the largest layer of Earth by volume. And then we have the crust, the lithosphere, which is the crust and the kind of upper part of the mantle. So we have this thin little crust on the outside. So what's causing that thin little crust on the outside of Earth to break up and move around? Well, in order to create a force, there has to be an interaction. In order for something to move, there has to be some sort of interaction. Well, what is interacting with the crust that could make it move? What's interacting with the surface of the Earth to make it move? Well, really, there's only one thing. Well, there's a couple of things touching the crust. Is it the atmosphere or is it the mantle? What could it be? What could it be? What could it be? Well, some people might say, well, the atmosphere, the wind blows. Well, you gotta remember how large continents are, how big they are, how massive they are. Yeah, the wind blows, but does it constantly move you around? You know, maybe a day or two a year it's really windy and it kind of might jostle you around a little bit. Other than that, it's really not pushing you around too much. So do you think the atmosphere and the wind could push around continents? Probably not. So what's the only other thing interacting with the crust? Well, the mantle. The crust is sitting on the mantle. So maybe something that's going on in the mantle is driving plate tectonics. Well, to understand that a little bit better, what we can do is look at a lava lamp. So, maybe some of you have a lava lamp or had a lava lamp in the past. Let's see here. Tricky. All right, so it's a little warm, but here's a lava lamp. Here's my lava lamp. All right, you can see the material. It goes up, and then it comes back down. And it goes up again. Let's see, is it going to go? Go. It wants to. Yeah! It goes up, and then something comes back down. Well, that's not unlike what happens in the Earth. So what's causing this process? Now, this is very warm. What's causing this process? So it must have to do with whatever is very warm in here. All right. Typically at the bottom of a lava lamp, you have a light. On top of it, this glass bottle filled with liquid. I believe it's some sort of oil. And then you have this waxy stuff. So what happens to wax when you heat it up? What happens to a candle? It begins to melt, kind of liquefy. Well, how is what's happening in a lava lamp similar to what's happening inside the Earth? Well, the process is called mantle convection. So let's talk about how a lava lamp works. So you have some sort of light, heat source, and it's heating up the glass jar. In that glass jar, in fact, at the bottom of the glass jar, I don't know if you'll be able to see this here. A little bit. In the bottom of this glass jar, you can see this kind of ring. That's a spring, like a spiral metal spring. So the light, the heat source, is heating up that spring. That spring is then heating up the wax. And when things get hot, it becomes less dense. Think about a hot air balloon. When you heat up the air, turn it hot, hot air rises. What happens to cold air then? If hot air rises, cold air sinks. Same thing in most materials. So when you heat up the wax, the hot wax rises. As it gets further away from that heat source, it cools down and it begins to sink. Same thing is happening inside the Earth via a process called mantle convection. So there's some sort of energy source, heat source in the Earth, causing material to heat up. That hot material becomes less dense and rises towards the surface. As it gets towards the surface, it interacts with the crust, cools down because it's far away from the heat source, so it cools, becomes more dense, sinks, heats back up again, and that process happens over and over and over. Same thing happens when you're boiling a pot of water to try and make some delicious macaroni and cheese. You have some sort of heat source, it's heating up the pot heating up the water, that hot water rises. As it cools down, it kind of sinks back down, and that process starts all over again. So you got water rolling in your pot. That's where that term rolling boil comes from. So this is convection. So Earth's internal heat is kind of causing the same process, this convection process, a form of heat transfer in a fluid medium by circulation of currents from one region to another. Another way, that's just a fancy term of saying heat being transferred to move stuff around. Right? So what's happening inside the Earth? So you have some sort of heat source within the Earth, more on that in just a second, heating up. So you have the hot inner core, which is heating up the outer core, which heats up the mantle. Mantle material, again, hot, mostly solid. Think about hot Play-Doh mixed with rocks, but still, you heat it up, it can move a little bit. So the hot mantle material becomes less dense than the surrounding mantle material and will rise. So you have this hot mantle material rising. As it cools down, it sinks and it kind of peels off in two directions. Now remember, this is hot, sticky, kind of Play-Doh-y mixed with rocks material. So as that hot mantle material is getting towards the crust, and as it cools down and sinks, it's really hot and sticky, and it kind of grabs this material, grabs the crust and starts to move it. It spreads it apart. In other places, it just crashes it together because it's so sticky and thick and hot, sticky, rocky material, mostly solid, and just kind of grabs onto this material and takes it with it in its journey back down. So that cold mantle material sinks back down, heats back up. That process happens all over again. Again, movement happens very slow. Remember, the plates move as fast as your fingernails grow. That's how fast the mantle material moves. Again, it's mostly solid, but it's all driven by this heat source within the Earth. In a lava lamp, we have the light source, so that serves as the energy source of heat. So, what's causing the Earth interior to heat up? I wonder. Can you think of anything what might cause the interior of the Earth to heat up? Or why is it so hot? Ever thought about that? Well, there are three main sources of heat inside the Earth. One, there's still some heat left over from when the planet formed and came together, accumulated, which has not been lost yet. Even 4.56 billion years into the future, again, the Earth was so big, there was so much collisions happening. Remember, they started off with small little pieces, the bigger and bigger and bigger and bigger and bigger just get squished together. The early Earth was just a hot, molten rock of heat and lava and magma. And as the Earth cooled, the outside cooled, but a lot of that heat is still retained inside the Earth, believe it or not, even over 4 billion years into the future. Now, another cause of heat in the Earth, stuff is moving around. You do have a liquid outer core that moves around. You do have mantle material that moves around, which is mostly solid. So you have frictional heating. It's the same thing when you do this. All right. When materials rubbing against one another, there's a process called friction, heat is generated. So you get some of that as well. And that's caused by as the mantle material cools, it becomes more dense, kind of sinks back down to near the outer core. But anyway, that movement of material down and up is causing that frictional heating. And then also heat from the decay of radioactive elements. Now, inside the Earth, There's a lot of different stuff, a lot of different material, a lot of different elements from the periodic table, if you've ever taken chemistry. Some of those elements are radioactive. And radioactivity is when certain radioactive elements decay. They spontaneously just break down on their own. When they break down, they're releasing particles in energy in the form of heat. So, heat left over from the formation, heat caused by friction, and heat caused by these decaying radioactive elements. That's where that heat is coming from. So now we know kind of that what's the heat source and what's driving this mechanism, this mantle convection, to cause plate tectonics. So we have heat radiating, being conducted to the outer core being liquid, solid inner core, liquid outer core. The heat is being convected to the mostly solid mantle. It does flow a little bit, but think hot, sticky Play-Doh mixed with rocks. So there's some movement to it, but it's more solid than anything. So that heat is being transferred up to the surface. That hot material is kind of moving up. As it gets further away from the heat source, it cools down, sinks back down, creating these convection currents, convection cells. When that hot, sticky mantle material interacts with the plates, it just grabs onto it and just kind of moves them all around. And then that heat transferred to the surface out into space. So in summary, I'm just going to read a few things here kind of quickly. So plate tectonics is the theory, highest level of knowing, that Earth's outer shell is divided into several plates that glide over the mantle. That's the rocky inner layer above the core, mostly solid. It's a unifying theory of geology, meaning that plate tectonics helps to explain just about everything. Volcanoes, earthquakes, rock cycle, you name it. How oceans are created, how continents are created. It's just all tied back to plate tectonics. The plate tectonics as a theory was finally, so the evidence and everything coming together was developed from the 1950s. If you watch that video, that Pangea, right? Harry Hess in the Navy in the 1950s started that current proof with seafloor spreading, and then on through the 1970s with additional evidence from the past of Pangea. So plate tectonics is the modern version of Alfred Wegener's just concept of continental drift. Again, Wegener didn't have an explanation for how continents could move around the planet, but we do now. The driving force behind all of this plate tectonics is convection in the mantle, so mantle convection. So hot material near the Earth's core rises and colder mantle material sinks down. So the heat inside the Earth from the core, left over from when it formed, from friction, from radioactive decay, heating up eventually the mantle material. Hot mantle material rises, sinks back down. That's what's driving plate tectonics. The convection, this mantle convection process, it drives plate tectonics through a combination of either kind of pulling crust apart. Those are known as divergent boundaries, more in that next section. Or sinking downward and crashing things together at places called convergent boundaries. More on that in the next section. So that's just a brief summary of what's driving plate tectonics. Mantle convection, that's the process driven by Earth's internal heat. So we're going to pause there. When we come back, we're going to talk about how mantle convection moves these plates around, and when these plates now interact, what type of boundaries exist between these interacting plates as they're moving around Earth. I'll see you back here in just a second.